Hi everyone. So welcome back to the course Mastering Computer Graphics from Pixel to Virtual Worlds. So far we have studied how visible surfaces are identified in 3D scenes. That is what 12 algorithms we discussed. So however, simply determining the visible surfaces is not enough for realistic images. So to make the objects to appear in more realistic, so we have to identify how the lighting is actually the surface, the shadows, the background, the highlight for the object, how the color can be applied in different lighting conditions. So these are all things to be considered for image generation in computer graphics. We call that as a illumination and surface rendering. The lighting side is called as illumination, and how to represent the object is called surface rendering. So in today's session, so we'll be discussing the light sources, reflection models, the illumination models, intensity attenuation, color considerations, half toning, dithering techniques. So these are all things we will be covering in this session. So coming to the illumination models. Illumination models, it describes how the light interacts with the object surface. That is what illumination. The purpose is to calculate the intensity of a light. That's what illumination reaches the viewer from every visible point on the surface. Rendering algorithm is uses these intensity values to generate the final image. In simple terms, I can say the illumination model calculates the light intensity, and rendering method is displaying the calculated intensity in a surface. So together, the illumination model and rendering model produce a realistic computer generated images. Okay, that is what the illumination model. So coming to the light source, so light is essential for visual perception. So when a light strikes on an object, the part of it's reflected and part of may be absorbed or refracted. So the reflected light reaches our eyes and allows us to see the object. This is the general principle. So there are two types of sources involved. One is light emitting sources, which is one light emitting, like a bulb or LEDs or sunlight, whatever it is. Second one is reflecting sources. So these do not emit light, but they will reflect the light. Walls, tables, books, sometimes human faces. So the total illumination can see by the viewer the combination of the light source and reflected light from the surface. Okay, you can check out this. So I need a light to see the object. I need a reflected light to understand what is the object. So that is what. And point light source. So the a point light source emits the light equally in all direction, omnidirectional, from a single point. Okay, even though if you put the light bulb, so it emits light in all directions, even the candle flame or small LED light. So the light rays diverge outward from the source in all directions. Since the source has a specific location, the direction of light reaches each surface point changes continuously. Okay, so the point lights are commonly used in computer graphics because they closely resemble many real world lighting situations. So next is the distributed light source. A distributed or directional light source emits a parallel light rays. Okay, so the source assumed to be infinitely far away. Therefore, all the rays travel in the same direction. Okay, so even though sun is extremely large and far away, so the rays are appear parallel when they reaches the earth. So the directional light simply illumination calculations are and widely used in outdoor scenes. That is what distributed light. And next is materials and reflections. So different materials respond differently when the light heated on its surface. Sometimes shiny materials reflect the large portion of incident light. You can take mirrors. any polished material, glasses, so they will reflect large portion of light. Some dull materials also there, so they reflect very less light and they absorb more light, like any wood material, wooden table or wood cloth. So these are all will not, even soil will not reflect material more, they will absorb more. Okay, sometimes the transparent materials particularly transmit the light while also reflecting some portion of light. So understanding the material behavior is important for realistic computer generated image rendering. Okay, so in that, let us see what is diffuse reflection. So it occurs when light strikes a rough or grainy surface. Some part of light is scattered actually. Okay, scattered uniformly in all direction. That is what called as a diffuse reflection. Sometimes it may happen while the light hits on the wall paint or clay. So because of the reflected light is distributed equally, so the object appears to be equally bright from every viewing angle. Okay. So the color we perceive for the most everyday object is primarily due to the diffuse light diffusion or diffuse reflection. Okay, so the surface appears equally bright and appears bright in all viewing angles. That is what the diffuse light reflection plays a role over there. So next is specular reflection. So it produces the bright highlights. So incoming rays of light is going to be reflected at just one point, and it occurs when light is reflected in a preferred direction than the scattered uniformly. So it is reflected. Polished surfaces, it could be anything, sometimes some metal uh, objects, sometimes even water surfaces are where you can get a bright spot absorbed in shiny surfaces called highlight. Sometimes specular reflection is responsible for making object appear glossy or shiny. Okay, so next we'll see components and reflection. So, the most illumination models combine three components: ambient, diffuse, and specular. Just now we saw ambient means a general background illumination. That is ambient, and that is you can check out the image. So this darker portion is actually ambient, and next one is diffuse, scattered reflection. So light is incident in this place, so it is reflecting partially and uniformly. That is what scattered reflection, diffuse reflection. And in this one, specular. So mirror like reflection is called a specular. So total incident of light is reflected. Okay, so that is what the components of reflection. Let's see what is ambient light in depth. So ambient light is represents indirect illumination present throughout the scene. Okay, right, light reflected from walls, scattered from nearby objects. So it doesn't have any specular specific direction. It doesn't have any position, and even it is having uniform intensity. So its purpose is to prevent completely dark regions in rendered scenes. That is what the purpose of the ambient light. So the ambient illumination equation can be written as I equal to Ka into Ia, where K is the object basic intensity, and Ia is incident ambient light intensity, and I is the resulting intensity. Okay, so that is what ambient light. Next, I will say diffusion. Diffusion reflection follows the Lambert's cosine law. So, with respect to this Lambert's cosine law, the amount of reflected light depends on the angle between surface normal vector and the light direction vector. So, n and l. So, based on the n and l, it is going to vary. So, when the light strikes the surface directly, so the surface appears bright. As the angle increases, the brightness decreases. So, this relation is proportional to cos theta. Okay, so you can check out this picture. Okay, right. So here the ideal diffuse reflections are called Lambertian surfaces, maybe a matte paint or chalk or concrete. So these are all they diffuse the reflection. These surfaces scatter the light equally in all directions, and the appearance does not depend on the viewer's angle. So wherever you can view, it's going to be same for all angle. So this property simplifies the illumination calculation considerably. Okay. So next is uh, combined ambient and diffuse reflection. So all surfaces remain visible. Okay, all surfaces remain visible, and it proper shading effects are produced. So the resulting intensity depends on the ambient coefficient theta and diffuse coefficient the diff, and light intensity I, and the angle of incident theta. Okay, so based on that the intensity actually differs. So combination of forms basis of many graphics rendering system. Okay. So next is specular reflection and Phong model. So so when we see a bright spot, that's what is specular reflection. So diffuse reflection alone can't produce the shiny light. Sometimes we need uh, a mirror-like reflection. So for that, we actually the Phong reflection model is used. So Phong introduced the method to calculate the specular reflection mathematically. This model considers the light source, surface normal, reflection direction, and the viewing angle, viewing position. So when the viewer direction aligns with the reflection direction, the bright light is actually appears. Okay, so the glossy surface generally produces this one. Okay, so that is what. So here the Phong model uses the angles R, V, right? R is nothing but ideal reflection direction, and V is direction towards the observer. So the specular intensity depends on the V and R. Okay, V and R. So you can check it over here. So R is the specular reflection, and L is the point to the vector toward the point toward the light source L, and V is the viewer surface position, and theta is the viewing angle, and R is the reflection angle. So that is what for an ideal reflector, the incident angle reflected only on the specular reflection. In this case, we would see reflected light when V and R coincide, which is theta equal to 0. Okay, so that is what Phong model. Okay, so when the shiny surface is modeled with a large value of n and s, say 100 or more, the small values are used duller surfaces. Okay, so the n actually check out this equation. Cos theta equal to dot product of n and l. So before that, we are having one equation. Yeah, these two equation. So with that equation, we'll be calculating the intensity. So intensity based on n and s parameter. So it is determined by the type of surface. Okay, so specular reflection coincident curve and k is equal to the some value 0 to 1 when very shiny space is there. So we'll be having a large value of n and s. Okay, so if it is dull value now, we'll be having less value of n and s. So based on that, we'll be getting the shiny or glossy reflection or specular reflection. Okay, that is what. So next model is one model. So one model is extension of Phong model where yeah, where it is designed to simulate the studio lighting effect, spotlight simulation, directional simulation, etc. And here we'll be talking about intensity attenuation. So light intensity decreases with the distance. So this phenomenon is called as attenuation actually. So according to the law of intensity. So light intensity is inversely proportional to the 1 by d square, where d is the distance from the light source, right? So therefore, the nearby objects appear brighter, and the farther object, distance object appear dimmer or very dull. Okay, so that is what. So here, f of d is used to calculate the value. So 1 by a naught plus a1d and a2d. It's a quadratic equation, and user can fiddle with the coefficients a naught, a1, and a2. So variety of lighting effects can be seen. So with the given set of attenuation effects, we can limit the magnitude with the function f of d, minimum of 1 comma the value. Using this function, we can write our basic illumination model with the intensity I equal to KAIA and all these things, N and H, L vectors, but D is the distance actually. Okay. So that is what, so ultimately we'll be calculating the intensity of the light. So that is deciding the reflection or diffusion or whatever it is. And next is color consideration. So until now we consider only the monochromatic lighting. But in real world graphics, we need to discuss about the colors. So computer graphics commonly uses the RGB model. Many color models are there, RGB, CMY, many models are there. So the reflection coefficients are defined separately for each color component. Okay. For example, the diffusion reflection coefficient vector RGB is KDR, KDG, and KDB. So if you want our object to a blur surface, we select a non-zero value in the range from 0 to 1. So blur effect reflectivity component KDGB can be given. So remaining will be set to 0. Okay. And any non-zero red and green components incident light can be absorbed. So the intensity calculation is given with this equation. Uh, so with that, we can calculate the intensity for any color. So for example, for a blue color, so it's IB is actually for blue color intensity. So with this equation, we can calculate the intensity to blue color component. So based on that, the blur effect or the color effect can be given. And these are all the various parameters and its uh, meanings are given over here. Just go through. Okay. And next is half toning under dithering. So in modern display and printers, we have limited intensity resolution. So this limitation causes the quantization error. Okay. So quantization means artifacts due to limited intensity resolution. Uh, to reduce the visible artifacts, we can use half toning and dithering. So these techniques used to create a illusion and smooth intensity transition. Okay. So let us move on to the half toning first. So this is the quantization errors. Images with the decreasing bits per pixel. See how it is with 2 bits per pixel. This is going to be an image, and 256 bits per pixel. This is the smooth image. Okay. So that's what quantization error. And coming to the so reducing effects of quantization. So we'll be having half toning and dithering. So these techniques reduce used to create a illusion and smooth intensity. So classical half toning or error diffusion dithering or random dithering, order dithering are the some categories in the half toning and dithering. We'll see it one by one. And coming to half toning is widely used in newspapers and magazines. So although only black ink is used, different shades of the gray produced by varying the size of the intensity of the dots. Okay. Sorry, density of the dots. So our visual system averages these dots and perceives the intermediate shades in between. So these techniques allows the grayscale images to be printed using only black and white dots. This is what called as half toning. Let us show the image, you'll understand easily. Check out this image. So this image is actually displayed with the, printed with the white and block dots. Okay, so that is what called as off toning. So different shades of the gray is actually generated by using this uh, technique. Okay. That is what half toning. The process of generating the binary pattern black and white dots from image is called as the half toning. That is what I told you, right? If the for example, different screens can be used to control the size and shape of the dots. Okay, a fine grid called a screen frequency 200 to 300 lines per inch can be given an image quality, depends on the resolution. A screen frequency of 85 lines per inch is acceptable for the newspapers. So that is what creating this kind of, if you zoom and see the image, you can see this kind of dots in the grayscale, black and white. It's called as half toning. So here different variations in the half toning dot size in the printing. You can check out. So the first one is some the dots size is higher, less dot size, and less dot size. And more dots is providing a more smoother images. Check out the various dot sizes as given for half toning the images. Next is patterning. So patterning is a simple digital half toning technique. So each pixel is replaced by a small binary pattern. Okay, different patterns represent different intensity levels. As intensity increases, the more white pixels are included in a pattern. So check out here, intensity ranges from 0 to 2. So here 0 intensity, I mentioned zero pixels, nothing is there. 1 pixel is used to represent the intensity, 2 pixel and 3 pixel, 4 pixel. So this intensity, sorry, varies from zero point 0.8 to 1.0. So um, pixels are used to represent the half toning in digital. That is what called as patterning. So which is replacing each pixel by pattern from a binary font. Check out this one, a 3 by 3 binary font for printing grayscale. So 0, 1, 2, 3. So pixels are actually used to print uh, font. Okay. So here an example of patterning. The first image is actually 8-bit image, binary image, and this one is half-toned image. So next is dithering. So dithering distributes the quantization error among the neighboring pixels. So instead of abrupt intensity changes, the errors spread across the image. That is what this dithering. So this creates a smoother visual transition. Uh, it's right. So all errors can be rounded off. Sometimes in dithering can be used in audio also. So human eye blends the variations into continuous tones. That is what actually the technique behind the dithering. So you can check out the dog image. So grainy. So let us see the. So here in dithering, error diffusion actually applied. So error diffusion distribute the quantization in error of the current pixel to the nearby pixels. So the errors are distributed to the nearer pixels. Alpha, beta, gamma are the different errors are distributed to the next pixels. So check out this image. So where you can see the dithering are reducing the errors to the surrounding pixels. So 8-bit and only 1-bit quantization. So Floyd Steinbeck algorithm and dithering 1-bit, and Floyd Steinbeck algorithm 1-bit, pure black and white. So the errors are distributed to the surrounding pixels to round off the error. Okay, and so this is the randomized quantization errors. Errors appears as a noise actually. You can truncate with the noise with the quantization, and yeah, this is the randomized dithering by the original. This is the original image. Uniform quantization with the 1-bit and the random dithering. So randomly you will be adding the noise to the image, and adding the rounding of the errors. So next is ordered dithering. So ordered dithering is used as a threshold matrix called dither matrix. The pixel intensities are compared with the matrix values based on the comparison. So pixels are rounded up or rounded down. That's what ordered gathering. So here the matrix Dn is called as dither matrix. So it may contain n cross n elements. So for example, at the second level D2, this is the matrix dither matrix. For D3, this is the dither matrix, and for D4, threshold matrix is going to be this one. So so we can calculate the reference position in the dither matrix with this equation. So I and j will be two entities. So with that, we can calculate the position of the reference position of the uh, every pixel in a dither matrix. Okay, so either you can round up or round down. Okay, so so this is the generalized equation for nth number or nth dither matrix. So fourth dither matrix. So another method for diffusing method for mapping the picture with the m cross n points with the m cross n pixel is called as error diffusion, and variation in the error diffusion method is called as dot diffusion. Okay, so error diffusion, random dithering, ordered dithering. So various ways to quantize the error and rounded off or nullify the error with the surrounding pixels. Okay, so this is the ordered dither, 8 bits original image. The first one is a original image, only 1 bit quantization, and the 4 cross 4 ordered dither image. So check out the smoothness of the image comparing to the uniform quantization, somewhat better. So here the original image, random dither, ordered dither, and Floyd Steinberg. It's algorithm, another algorithm dither. So various images represented with the dithering. Oh, sorry, single image with the various dithering approaches. Right. So with that, we are completing the topic. So we in this session we discussed the light sources, materials, ambient, diffuse, Phong model, Wan model, intensity attenuation, dithering, and all we discussed. So with this lecture, I think we are completing the study of visible surface reduction and illumination models and surface rendering methods. I think these concepts are very fundamental to the computer graphics, animation, and game development, virtual reality, and the visual simulation systems. So thank you for your attention. See you in the next subject or next uh, any new topic. Happy learning. Thank you all.